Hello everyone, welcome back. This is going to be a short lab focused on Linux virtual memory. The goal in this video is not going to be explain every aspect of virtual memory, of course, because we took some time explaining some of the concept. To be honest, there is many things that I forgot to mention in that video, but I was thinking maybe if I'm not going to be able to highlight those concepts in this video, maybe in the next video videos, I would mention those things uh, whenever I found the time to do it, or if we face something that related to it. Okay, but as I said, um, in this video, I intend to show you how to approach a memory pressure the way a performance engineer would. We're going to move from one command to the next, letting each observation guide us to the next step. The idea is simple. Don't guess. Base every decision on data and evidence rather than just guesses and hunches. So to make things interesting, I'll use memhog to create artificial memory pressure around the system. But here's the catch. We are going to pretend we don't know. Okay? So imagine you've just received an alert. There is an issue on your server. You don't know if it is a CPU, if it is a memory. You have no idea actually. But the client is complaining there is latency or there is uh, they're not happy with the servers. Okay, so where do you start? Which command do you use first? What do you look for? And how do you know whether you're looking at memory leak, happy allocation, swapping, cache, growth, or something completely different? As we investigate, we'll build a chain of evidence. Every command should answer one question while raising the next, allowing us to narrow down the possibilities until we understand exactly what we have. Okay, that's the mindset of a performance engineer. Observe, collect evidence from the hypothesis, uh, verify it, and only then draw a conclusion. So let's get started. Before talking about the memhog, actually, there is something we mentioned in I think, the previous video. It was about the stack. I'm not going to take a lot of time in it. Just I want to show you what you expect from the stack issue. If you see this error, you know exactly what you have. Okay, so I have the script actually. Let me show you. Anti-rich, the stack overflow. Okay, before executing it, I want to show you this is actually an Ubuntu server. It is C star release. It's an Ubuntu server. Number of, sorry, MP, number of virtual processor are going to be 2, and our memory we only have 8 gig. So this is just a small VM inside my laptop. I'm not going to use the cloud or anything here. Okay, so as I was saying, -f, since we don't have the messages file in Ubuntu, we have the syslog. So let's see var log. Okay, syslog. Okay, let's execute. As you can see, you'll find segmentation fault, or what we call sig fault, or I think a signal 11. Let's see it here. So if you see this error, you know, yeah, that what's really happened. Your process is starting to allocate in some memory, but somehow you have a deep stack, which is why you have this error, because your system is not allowing the process to get more than 8 MB of memory. As we talked about the last time, if you check the U limit -a, you'll find out that you have this one. So what you could do right now, if you have this error, you just yeah, you just go into to adjust or to tune your stack. That's just so you when you see something like this, it's rarely happen actually, but if you see something like this, you understand that you have a stack limitation. So let's start with the memhog. Here I want to do memhog. Let's go. Yeah, let's take 8. 8 is good. But before that, I want to show you what memhog actually is doing. If you never use this tool, SREs. Okay, so there is if you want just to see how, not how, uh, you want to see if you did the CKS or you are preparing for it. For sure, you know this command. It's just going to show you all the syscall that you have in this command or script or whatever. Okay, I shouldn't do it like this, but yeah. Anyway, so as you can see, we are using the right syscall. We are using the berg. We understand what berg do. Berg just a pointer in your VMA, and we are reading. We are doing a map, open at, etc. So at least now you know exactly what your script or whatever is using as a syscall, so you can limit it uh, for a security reason. For example, if you are not here open any network, so you are going to make this script forbidden from using the socket. For example, people are using this command to understand what they exactly need. Yeah, so but I'm not going to use this command. I want more detail. So what I'm going to do, I'm going to remove the C. Exactly. So as we have seen, we are in this memhog. We are using map. We are not using our malloc family. Uh, there is something interesting here. Actually, I've seen it. Okay, as you can see here, we talked about this file. For some reason, memhog is opening this file. Actually, it is open to understand how many nodes we talk about NUMA node we have in this system. It find out that we only have one NUMA node, so it is going to allocate the memory accordingly. This is what exactly the memhog is doing, and here, as you can see, we are start allocating the memory, etc. So if I do this, memhog, let's go back. For example, yeah, let's use 4. I just want to have an idea. Let's say we don't know exactly what we have here. As we said, that someone is calling us, complaining about the system is slow, and we want to understand what we have. There is some command you might use, just is going to give you an idea what's your yeah, where or from where you are going to start. You can use so many methods here. For example, you can use a Brent and Craig method, the use method, utilization, saturation, errors, but I'd rather go simple. Just want to start with top. The system is freezing. Okay, so from top, I can see I have memhog. Memhog is in this state. It seems blocked for some reason. Maybe there is an I/O issue. Maybe there is a lock. I don't know. I have to investigate to understand. I can see the resident memory. It is reaching almost 2.6 in one memhog, etc. So it is almost 2.5 in each one. We have 3 right now. So there is actually a shared memory also. Let me check here. Just want to see. This is just a curiosity. It's not related. So let's see. IPCS, it is using shemam, or it is using MPFS. Let's see here. Dev shemam. No, so not a problem. Okay, so I thought I can add something to this lab, but it's okay. Um, as you can see, memhog right now it is in our state, the state again. So let's move on. So as you can see, it is in the state, and for some reason the CPU went down to 20%. Let's see with mstat how much it is in user space and how much it is in system space. Okay, something interesting right now I can see. It seems the memhog went already finish. No, still. Let's see. PS, ef. Grab memhog. Okay, it's done. Let's do it again. Let's do it here. Okay, how much of them I have right now? Okay, we have 4. It's enough. So let's do the MP stat again. Let me see what I have. So the system time is high, but the user time is not almost nothing. So the CPU is spending too much time on the kernel space. So I need to know exactly what the kernel is doing right now. Is it doing something meaningful to me? Uh, it is doing read write, or it is doing something that is not meaningful to me, which means that wasted time. I need to understand that. Okay. Before that, I need to just to collect some data. I need to understand because, as you can see right now, I have the IO weight is very high. So I need to understand if this is just an IO or it is locked for waiting spinning for a lock. If there is a lock contention, I need to understand that. So just need to collect some data. For example, let's see star dash R1. Star-R1 is going to give me more information as as we talked about from free dash H. As you can see, we can see from here, for example, the cache. We can see the buffer. Uh, we don't have a raw IO right now. We can see the active from inactive. This is we talked about. We call this the LRU, if you remember. The dirty we have almost nothing. Available we have nothing, not almost. Memory used is 97. So let's see star-b, because sometimes even when you have your memory is 90% or even 100%, that doesn't mean you have a memory pressure. Sometimes you are using your resources perfectly, so you have enough you have you are, even though your utilization is 100%, doesn't mean you have saturation. That's what I'm trying to say. So let's say with star-b, let me first check if okay, we still have them. Okay, so I can see here, let me show you this. Just take a screenshot. Okay, just want to explain some things. For example, here we talked about it, but let me explain it again. We have this one. Okay, what I'm doing right now. Okay, let's do this better. Okay, so I want to explain the major fault. So imagine here you have disk, okay, and you have your memory, and you have your CPU. So it is simple. Your CPU is trying to look for some data from the memory, but the CPU can find it in the RAM. So what the OS is going to do, the OS is going to take over and try to upload the data from the disk. Let's say this is the file. It's going to upload it to this disk. So right now you are in the mercy of under the mercy of the latency of your disk. If your disk is HDD, then you are in trouble. There is too much latency here. Okay, so anyway, what I'm trying to say that the major fault is when you can't find the data in the memory and you have to go to the disk to upload it to the memory. That's called major fault. And you see here we have some data here. Okay. Why this is a problem? If you have memory pressure and you are swapping and you are discarding from the LRU, as you know, the anonymous page is not part of the LRU, so you have to swap it. And for example, let's say you have a clean files, you discard it, so you have to take it again from your disk. So it could be a problem here, but and also I can see you have not a huge, but you have amount of minor fault. Minor fault usually it is TLB misses, but I don't want to jump to any conclusion. I need to make sure that this is what's really happening. Okay. Also, we have a page out and we have a page in. Okay, so there is something some people might not know, but let me explain it here. This is what we are doing right now. Okay, so here we have the page in, page out, and if I do star dash capital W, I can see swap in, swap out. It seems that we already, let's see how much we have. Grab memhog. Okay, we have 4 of them. So as you can see, after I enabled the memhog, or I started the memhog, I can see there is a swap in, swap out right now. This is a trickle swap, which is should be an issue. I need to explain what is the difference between page in, page out, and swap in, swap out. If I do it like this, okay. So as I said, imagine you have a disk here, and you have this part is just the swap, okay. So this is your memory, and this is your CPU. I'm sorry for my drawing. It's okay. CPU. Okay. So page in, page out is let's talk about page in. Page in, for example, let's say you have a file here, and this file you are loading it because there is a major fault from the disk, or you already have some data swapped to the disk, and there is something called a refault. I hope we talked about it last time. Refault. This concept, I'll check if we didn't talk about. Maybe the next one I'm going to mention it. Okay, so let's say there is a file here. You load it from major fault. You load it from the disk, or there is already a page swapped to the swap, and you are taking it back, which called refault. You are taking it back to the RAM. In this case, this called page in. So the file from the file system or the file from the swap or the page from the swap is taken back to the RAM. Both of them are page in, but the file from the file system it's not called swap in. So the swap in is only when we talk about the swap. So this is the page swap in is part of the swap in. And the same concept is for the page out and the swap out. It's the same thing. Okay, so when you swap out, you actually taken pages and push them or flush them to the swap. You can call it also page out, but when you take, for example, you have dirty file, it is not the same file you took it 30 seconds ago from the disk. It's not the same, so you have to flush it back so you can have the same file in the memory backed on the disk. There is two things that trigger the write back. Actually, there is the 30-second, and if the dirty are reaching 10% of the data. You can't have more than 10% of the data dirty. Okay, we'll talk about those things later. So, as I said, this is the difference between page in, page out, and the swap in, swap out. So page in, page out is more is including page swap in and page swap out. Anyway, uh, let's do it again. Let's see if we still have it. Okay, let's do this. My system is frozen, but it's okay. Let's see if we still have the memhog. We have two of them. Okay, so first of all, we try to have a general idea or the full picture. What not the full picture. We just take a glance on the system, what we already have, and we see from the top we have some process that is taken some memory, which is in D state. In that case, since we have the D state arisen, we are seeing that the load averages goes up. Whenever the load averages goes up, that means we have the system is not going to be accessible as it should. You might face some latency. You might have some calls. So yeah, so we took top. Then since we have seen the D state, I want to know if my CPU and the load average goes up, as we said. I want to know if my CPU is, as you can see here, we can see it from here, is 33%, but I want to make sure what I have in the system time and what we have in user system space, what we have in user space. We found out that we have pretty high system time, and we have the IO weight is also high. Okay, so we want to understand exactly why our system time is high. Is the kernel doing some work for my process, or it is busy doing some unmeaningful work? Okay, so let me do this again. After that, we just want to collect more data so we can build the hypothesis. We have seen that our memory is full, so the utilization from if we are going to use the Brendan Gregg method, the use method, so the utilization is going high. It is almost 100%, but that doesn't mean we have a memory issue, as I said. So we need to know exactly if we have a saturation issue. We checked. We found out that okay, so if we take a look at this, also we mentioned that we are going to talk about the commit later, but in the same time, I need also to explain those one, but not right now. This video is already a bit long, and yeah, people don't watch long videos, so I'll take my time to explain those things also. Not yeah, because that's very important, but not right now. Okay. So we checked if we have a memory pressure. we found this one. We found out that there is a memory pressure. We have a major fault. We have minor fault. There is a swap page in, page out, swap in, swipe out, as you can see here. Well, to be honest, I don't care about the swipe out because this is usually asynchronous. The system, my process is not affected by this, but this one is actually a problem. If this is going to happen a lot and frequently, that means that my system is going to suffer. There is actually something else. You know what? Let me explain this. Just let me take a minute or two explaining just those two part, because I've seen so many engineers don't know what the difference between the even experienced one. To be honest, there is people are maybe better than me, but they don't know the difference between this and this. Okay, let me explain the difference between these two. So I think you already seen this when we did top. I think I've seen it. Yeah, you can see keyswap D is triggered. That's mean you have memory pressure, but you didn't want to check not memory. Yeah, not. But what I mean is that my system is trying to to reclaim some memory. Okay, let's say it this way. So keyswap D is already triggered, and this is actually happened because we are reaching some limit, if I can say that. Okay, so usually what happened, the system asynchronously asynchronously trying to reclaim some memory. So your process, if your process asks about some memory, it can find it without any issue. This is called fast path. Fast path. Maybe we are going to explain it later, but there is something called PCP. I don't want to extend here. PCP list. Each core has something called PCP list, which is basically a memory. Usually in the latest kernel, it is 0, 1, 2. Basically, it is 4K, 8K, and 16. Okay, so what does that mean? We have 4K pages, 8K pages, 16 pages. If you are asking for something in this range, you'll find it without any issue in the PCP list. Each core has its own PCP list. So each core is going to have this one. This is called fast path. When the process asks for any memory, if this is already if the PCP already list is not it's not empty, yeah, the process will be able to get the memory without any issue. But if I'm not going to talk a lot about this, leave this later. So, but if your memory is not able to get any space in the RAM, so what's going to happen? The key swap D, as we talked about, since we only have one NUMA node here, the key swap D, as you saw from the top, the key swap D 0 is triggered and it's trying to reclaim some memory. It depends on the how you tuned your system, but usually it's going to start from the slab, then to the inactive file, etc., etc. We talk about this a lot. Okay, so why I'm saying this, I need to explain the difference between the PG scan K, and this is actually happen asynchronously. The process is not, your process is not concerned about this one. Okay, this is called PG scan K, which is mean it is using keyswap D. Okay, but the problem is with this. When you have a lot of how I say it, when you have numbers like this in PG scan D, that means that the process, let's talk about this, the process is asking for memory, but it is not finding it, so it sleep on the kernel. sleep on the kernel. The kernel right now is taken over, trying to reclaim some space and and trying to reclaim some space. And the whole time when the OS or the kernel is reclaiming the space for the what the process asks for, the whole time the process is sleeping. So there is serialization here. So this is actually a terrible for the performance. So this is not asynchronous, this is synchronous. I hope you understand the difference. This is actually not good. So I don't want to talk right now about PG free and PG steel and this one. Let's leave it later. So as I said, we start from top. We went from top to memstat, so I can see it clearly exactly how much I have from my system. I have an user space, system time, sorry, and the IO weight. I already have a theory in my head. I want to make sure that this theory is right or wrong. So I'm suspecting something, but I don't want to jump. Let's build it on the data. So just check the memstat, as I said. The system time is high. I want to see my memory. Because of that, I want to see my memory. I found out that I've seen some details. I usually, after sar-r, I usually use the cat prem proc meminfo, but right now it's not necessary. I see the sar-b to understand exactly if I have memory pressure. Right now, I can see there is major fault and there is minor fault. The page in, page out, there is some numbers here. I want to make sure that if I have a swap issue, I found out that my system is already have swap in, swap out. So let me do this. Okay, let's do for time. 1, 2, 3, 4. Okay, if I do, let me do it again. I can see. Okay, it start right now to swap in. That means I have a trickle swap. I care about this. Imagine your system is facing this pressure for a long time. It's going to be a lot worse, but yeah. So as I said, for now I need to make sure what my system time is. So what I'm going to do, usually I use this command perf top. Okay. Because my system is facing some memory pressure, of course, it's going to take some time. But it is collecting right now for some samples. Let's see. So I can see this raw spin unlock is taking 6%. The PV native safe hold is taking some time also, but I need to make sure there is this one also, the libc. So right now, let me do it this way. Let's see. Let's take the process. For example, let's take this one. Why not? Let's do perf report dash g dash p and put this one. Okay, let's do some recording. Sorry, this is report. Record. Okay, cool. Okay, they're still ongoing. Okay, this is perfect. I'm trying to exit. Let's see. You stop. What's happened here? It's taken enough time. It seemed to exit. Okay. Okay. Memhog swap D as usual. I have them in D state. Let's see what we have. Perf report. Okay. So let me extend this one. Let me plus, type another plus 91% plus plus. Let's see what we have here. 60%, 64. Shrink down zone. It's okay. I think this is enough for me. Let's take this one. Okay. Let's make it bigger so we will see it. So I can see from the perf command that we, as I was suspecting, I can see there is this ASM exec page fault. This one mean that we have TLB miss. Okay, TLB miss, which means the virtual to physical doesn't exist in the TLB yet. So what's going to happen is going to raise the CPU is going to raise an exception. The OS is going to take over and walk through the page table. As you can see, the user address fault, and now we have the PTE. We talk about the PTE. We said that there is the PG. What is this? There is the PGD to PUD to PMD. At the end, we have the PTE to look for the 4K, and we have the memory here, and this is going to point to your page in the physical. Right now, we are going to load it in the TLB. This is what really happened. After that, we have the do anonymous pages. We are trying to uh, this is called actually a reservation, and right now we are trying to allocate it. Okay, VMA allocate folio, allocate page and pool, allocate pages. Right now, the problem is right here. As you can see, every time you see slow path, that means that we have a problem actually to allocate some memory in the RAM. That means that we have a memory pressure, and the OS is trying to free some pages before it gives you your 4K. Okay, as you can see, after that you'll see try to free pages. So we have memory pressure, do try to free pages, and now we are shrinking. That's mean, as we talked about, we have the LRU list. Here we have the inactive, and here we have the active. So what your OS is trying to do is trying to free the inactive, so it would shrink the list so you can have some free space. Okay, shrink node, get page from free list, and we have get free from the free list here. Let me, even though we don't need to do this, but let me see what we have after that just to explain it. Let's do plus shrink many, shrink one. You see, we have tried to shrink the LRU vector, which is, no, I'm sorry. Let's do plus shrink folio list, And now we see page out. That means we are trying to swap. We are trying to take some data from the memory and we push it to the disk. So after that, we are trying to unmap that old data. We are resetting, as we talked about. We say, if you remember, we said that we are using as Berk, and Berk depends on what you are using to reset reset the pointer. For example, let's say this is the application memory, and you have as Berk point in here. So you are trying to reset it to point, for example, right here. Here we are talking about the heap, just so you remember. Okay. So try to unmap, as I said, reset the pointer, try to unmap, remove mapping, folio reference, rows pin lock. Now we're releasing the lock. So after all what we did, right now we are sure, definitely sure, that our system time that we are seeing is actually allocating time. We are facing a memory pressure. We weren't able to allocate our memory asynchronously. We are doing it synchronously, as you saw from the SAR, and also you saw from the perf. Right now we have the full picture. We understand what it is, what is it the problem, and yeah, I think we are finished here. We can we can base our conclusion on data, not just hunches and guesses, as we said. So hopefully this video was helpful for you. Hopefully you enjoy it. Thank you guys for all your support. At least the comment that I received on YouTube and LinkedIn. Thank you to encourage me. I really appreciate it. I hope you also share this video, and I hope you liked it also. If you like it, share it please, and give me thumbs up so I can so you can encourage me to keep the video coming. Yeah, thank you guys. Bye.